introduce Jarle to you. So he's assistant professor in Leiden. He did his PhD. Yeah, here we go. He did his PhD in Cambridge, UK, and then he went from Oxford to the Max Planck for Astrophysics in Garlic to Porto, and then he decided he had too much of the sun, and he decided to go to Leiden. And he is very well known due to his work in the Sloan Digital Sky Survey. If you do anything with Sloan on the local universe, you've come across him. And also he's coordinating all science that is not cosmology for Euclid, and Hans Walter was saying, no, okay. That's also a very interesting part of Euclid, as we should mention. And so we're very much looking forward to his talk and to his patience with all this kind of experimental setting that we provide in this really nice and old Herstal. So thank you for coming.
Thank you very much for the invitation. It's interesting to be in a sort of very an auditorium with a bit of patina. We don't have that in Leiden. Ours look like it's designed from the 70s Soviet architecture. This is a lot nicer. Now, what I'm going to talk about today is work also with using the Sloan, but what I'm going to talk about is a way trying to infer the gas content of galaxies at low redshift using optical spectroscopy only, which is a little bit heretic, I'm sure. I'm going to touch on a number of things today. So it's a small roadmap. Have a brief introduction, which is going to be also a bit interspersed with the talk at times. I'm going to talk about the modeling technique. This is a little bit dry, perhaps, but it is essential to sort of convince you that the rest of what I'm talking about even makes sense. I'll then talk about gas content and the time it takes to deplete that gas in the central regions of galaxies. And then I will talk about two specific things that follow from this, namely the mass-metallicity relation. I've done the standard thing of making a sentence ending with a question mark, and you know that in that case the answer to that statement is no. And then I'll see if I get to the final point here, because I'm not quite sure I will. I put the result in the roadmap, so now you see it. Hopefully I'll come back to it and convince you that makes sense. Now, why would we want to do this? Okay, so this is an image of the Milky Way, or rather a composition of many images of the Milky Way, coming from radio continuum all the way up in energy to gamma rays on the bottom. And this is what a galaxy looks like. Okay, it is a multi-phase object with emission spanning many orders of magnitude. Now, if you go out and you look at what we normally do for a distant universe, there is a tendency that we will focus only on a little bit of this, and a large part of what we understand about, or what we know about the distant universe, and even relatively low redshift universe, is really focused on these two bits. So the near infrared and the optical region. Now, there are, of course, exceptions to that rule, but that's very often the case. And so we know quite a lot about those aspects. Okay? So here's an example of what we call the spectral energy distribution fit. So wavelength on this axis, flux on this axis, and these orange points here is from work by Elisabetta Cunha, but at that time she was at IAP, now she's at IA. And these are flux points, and you fit models to this. From this, particularly in this region of wavelength space, you can then infer something about the properties of the stars in these galaxies. And so we know quite a bit about that. So it's not a talk about that, but just to give you an illustration of the kind of information one can get out now, here's results from a recent survey, or an ongoing survey actually called UltraVista, which is a very deep near-infrared imaging survey of the cosmos field. And if you just focus on the right-hand plot here, this plots as a function of the mass of the galaxy, how much mass there is in total in galaxies of that mass, okay? As a function of redshift. So as you go from early times in the universe, redshift of about 0.2, to the present-day universe, you see that mass in stars builds up, because stars form continuously, and many of those stars remain around for a long time, so the total mass in stars grows. So we can map that quite well, And that gives us one view of the galaxy population. And it's a very powerful technique, it's a very powerful resource, there's a lot of information we can get out that way, but it is an incomplete view of the universe. And in general, gas content is not something we do, not something we have or can routinely obtain for large samples of galaxies. There are what people working in the field call large samples, but they're not millions. These are hundreds of thousands. But that's crucial because gas is what stars form from. Gas is what massive stars ionize. It's what sells posters of HST images. It's also where the ejecta from dying stars end up. Okay? So it's an absolutely crucial ingredient in the life cycle of galaxies to understand the content of gas in these galaxies. So we really would like to have that knowledge. Now, how can you get that from large samples of galaxies and not 10, 15, 20 galaxies? So, because this is so central, there has of course been a lot of effort to work this way. So there is the Alfalfa survey, is one recent survey, using the Arecibo radio telescope, Puerto Rico. It covers a large chunk of the sky, covering this redshift range, so quite nearby galaxies. And they will get about 20,000 galaxies that they will detect. Good quality, where we also have other information. So this works quite well, but because it's selected as a limit in H1, it will only get gas-rich galaxies. So to complement this, we carried out another survey, which is really complementary, called the Arecibo SDSS survey, which was just a complicated way to get the acronym GAS. In this we actually also used the Arecibo telescope, but we targeted each galaxy and designed the integration types so that we would reach a fixed gas fraction limit for each galaxy. Okay. So then, in the other way, you get down to a particular limit in H1. Now we wanted to get down to a particular limit in H1 divided by mass. So we did that. That gives us a much better understanding of completeness and what happens in massive galaxies. There's a survey to get CERN to go with that. Now, so armed with that, you can then start to look at what does gas do in galaxies. And so here are some plots that tells some story about that. Focus on the red points here. There are some grey ones in the background, which you shouldn't worry about. Talk here. So here I plot on this side gas mass divided by stellar mass, mass in stars, and then here the mass in stars. And the green points are upper limits. And you see that as you come in mass, there is a correlation. It's quite with a large amount of scatter, and incompleteness is spread all over in mass. So mass doesn't tell you whether a galaxy has gas or not. If instead we plot on this axis the same y-axis, but now here we plot how much stars there are in the central regions of a galaxy, so total mass of stars divided by the size of the galaxy, well, then there is a different situation. Then you can actually predict which galaxies, reasonably predict which galaxies have no gas. So this was the starting point to get large samples to understand in gas ratio terms. But we really wanted to go past that. Yeah?
When you say no gas, you mean no cold gas?
In this case, I mean no cold gas. Yeah. So I'll talk about cold gas only here. Yeah, that's a good point, because indeed, what you probably is even more important than what I talk about here is to understand where the warm and hot gas is. But that I don't have any reason for. Indeed, many of the galaxies that have no cold gas might have a lot of hot gas. So this gas survey was very efficient at getting gas masses for massive galaxies, but still it took a lot of effort to get 1,000 galaxies done with Arecibo. Arecibo is big and not very steerable. But it was limited to atomic gas, and so we really wanted to go past this to get samples for larger samples. So it's then interesting then to just briefly remind people how you go about getting gas masses. So there are various ways. One is to use the 21 centimeter hyperfine transition hydrogen. That gives you a measure, and this is quite direct. It gets you directly the atomic hydrogen, as long as you're not in this regime where you have a lot of self-absorption. But in general for galaxies, this is very direct, it's very well functioning. But it isn't necessarily what you want, because stars don't form directly from atomic gas, and it is very challenging to do this this kind of survey work out to high redshift because of sensitivity issues. You also want to understand what's going on with the molecular gas. You cannot detect cold molecular hydrogen directly. It just doesn't have any transitions. So you need a proxy, and so the most common is to use CO, and then you measure the CO abundance, and then you convert from there to hydrogen, molecular hydrogen abundance using some sort of conversion factor, which typically gets parameterized like this, and some factor times the metallicity of the system, and then you can get a conversion factor. But that's tricky, and it depends on some uncertain calibrations, but it's doable. It's not direct. You're not directly detecting the bulk of the molecular gas. Yet another possibility is to model the dust emission. That's become very popular. Again, you can model the far infrared emission of dust, similarly to the SED model I showed you earlier, which actually did that. And then you can convert that dust mass to a gas mass using some reasonable assumption for the dust to gas ratio. So that's powerful. So there's a range of these techniques, and they cover various parts of parameter space. These typically molecular and atomic gas meshes all cover quite large spatial scales, and then there's a whole host of indirect methods, most of which I mentioned briefly. And I'm going to talk about dust absorption. Okay? Instead of dust emission, using dust skin absorption. And you can make a toy equation, just to illustrate it. So if I write down 1 over the gas content, well, it's the metallicity, the metals by the gas mass, the dust to metal ratio, which I'll call psi, and the dust attenuation, which we usually call tau. So we want to, if we can constrain those, and that of course is not a proper equation, but a combination of these quantities actually will turn out to provide some constraint on the gas content of a galaxy. Now, there is a side point here, which I'll just mention very briefly, and that's, if you recall, if you look at this one, for instance, this is a gas, solar metallicity gas, photoionized by some UV radiation, and these curves tell you how much cooling each element gives in total, and the black line tells you the total cooling curve, and that's effectively the energy loss from a gas. And so you see that various elements contribute to the overall cooling, but particularly if you increase the metallicity, well, then the cooling goes up, and the general temperature of the gas will generally go down slightly. And likewise, if you keep more or less the metallicity right, but you deplete some of these elements onto dust grains, so they just disappear from the gas phase, then you actually reduce the cooling and the temperature goes up slightly. So that is actually possible then to exploit and use to predict, see the effect on emission lines. So I'm going to show you that as a very tiny movie here. This shows an emission line diagram. Two line ratios on the x-axis, a line ratio on the y-axis. The colored symbols here are galaxies from the Sloan Digital Sky Survey. And now we'll see if this actually works. Okay. Here you can see this is how the model changes as you go up in metallicity. That's the track here. And now you see more tracks, and this is when I'm depleting more and more of the elements onto dust grains. And what happens is that the temperature goes up, but nitrogen, which is on this axis, does not go into the dust grains. So this nitrogen goes up in this direction because the temperature goes up, nitrogen emission goes up. So it's not as simple as that. There's a lot of there's various families of these models. These are different ionization parameters. So they can separate in certain parameter space. You can separate them. And you see the spacing is a lot bigger here, where what corresponds to high metallicity than at low metallicity. So this actually turns out to be the case that we cannot constrain the dust to metal ratio at low metallicities. Skip all that. So I'm not going to go through all the details of the model assumptions. We make a number, some that are a bit problematic, but we basically just assume that the galaxy, the stellar medium, is made up of Wilsonian distribution of clouds, and then make some additional assumptions on the properties of the dust, basically constrained by the optical attenuation curve, which is fairly well understood in galaxies. And you result, and I think the details of derivation are sufficiently, not every aspect might be fully defendable in isolation, so I'm going to not go through all the steps, but rather focus on the tests of the method in a second. And what you will find when you go through this is that this combination of the parameters, so this is the same thing I showed you earlier, but now with a proper scaling, can predict the gas surface density. That's the total gas surface density, and basically what I'm getting is this is the dust to gas ratio, is the denominator, and this is the dust is related to the dust mass. Okay. So it's sensitive to the total gas column, and the exact scaling relation in here does depend slightly on the dust moles, etc., but certainly the uncertainties are no larger than a factor of 2. And so to calculate that, what we do is we actually calculate a large grid of these moles, photoionization moles with various parameters, and we calculate the likelihood of each model given the data using an assumption of Gaussian errors, which seems to be reasonably good. And I've tried a number of these models. I'm not going to compare them here. I'm happy to talk about them if anyone is interested. But just to give you an illustration, this is for one galaxy. I have one line, and this is the likely distribution of dust attenuation, metallicity, ionization parameter, dust to metal ratio, conversion factor between H-alpha luminosity and star formation rate, and the surface mass density of gas. You will see 2 lines here. There are 2 different priors, just to test the dependence. And now I'm going to add lines, okay? Adding H beta, O3. Now I have 2 ionization stages of oxygen. Start to get some constraints on metallicity. And now I'm adding in hydrogen alpha. Well, there are 2 things we know from basic physics. One is that the ratio of these 2 Balmer lines is a good constraint on dust attenuation. And indeed, the likely distribution here is well peaked now. And the other thing is that now I can dered these lines. The combination of these lines is known to be a bimodal function of metallicity in some cases, and that's indeed what you see here. There's 2 possible solutions for the metallicity, so I need more information. And so I add in nitrogen. Okay, if you have a lot of nitrogen, it's high metallicity, and indeed that's what happens in this case. This is not a random galaxy, as you might guess. And in this case, you have an element that's not depleted on the dust grains, and you actually start getting a constraint on this dust to metal ratio and on the gas surface density. And then you also add in sulfur, but I'm not sure I believe that.
Well, can I just make sure I understood what I just saw? So without spatial resolution, measuring the strength of the nitrogen 2 line, all of a sudden gives you the gas surface mass density.
Yeah, essentially in this case, yeah.
In this case, that seems like beautiful magic.
So it doesn't work at very low metallicity. I'll show you that in a second. It works less well because I can't constrain the dust to metal ratio. So it is, in this case, yes, because it's temperature sensitive.
But the value it picks is not the most likely value you have in the previous distributions. Is that worrisome?
So that's actually why there are 2 different priors in here. And so I also sometimes try it with different other priors, but no, not necessarily. It's not a given that it's not a given that this will give you. Here there isn't enough information to give you a good constraint on the likelihood.
But
so,
if I don't have the nitrogen line, I will be usually off, right?
Yeah, that's correct. Yeah, that's correct. So there is one has to be a bit careful with not including objects without the necessary information. In general, anything that includes in this fitting that doesn't include a line that's non-refractory will generally be poorly constrained and useless. Because you need that particular information. Otherwise, it's too degenerate with all the possible solutions. So I'll apply this now to the Sloan Digital Sky Survey. I'm not going to talk about the SDSS. I'm just going to say I'm going to use this dirty purple region here, which is star-forming galaxies. I'm not going to discuss that in any further detail, just take it that those are star forming. One crucial thing about the SDSS, if you're not familiar with it, which is important here, is that the spectra are obtained in 3 arcsecond diameter fibers. Okay, so you have these small keyholes that are 3 arcseconds that you look into the galaxies through. And then we'll do work on this data, and then so you apply that to, this is about 200,000 galaxies, and then you infer what's the distribution. So I'll start out by the dust to metal ratio. Okay, so this is now the likelihood distribution of the dust to metal ratio as a function of metallicity. I've added in 200,000 galaxies in here, and this marginalized all metallicity. And as you see, the constraints are, there is a trend at high metallicity, and then here comes this situation I was saying, there is no constraint because all the models are degenerate at low metallicity. Okay, so metallicity is below 50% solar. I cannot constrain the dust to metal ratio. The likely distribution is almost uniform. So in these regions I need to use a prior. And there's actually what these 2 lines are. I'm not going to talk about them here, but those 2 lines provide priors that you can use to limit the extremes. But this is rarely used. Okay, there's a few papers that discuss the dust to metal ratio, but they're not many. But the dust to gas ratio, there's a lot. So people like to use that a lot. So I converted it into dust to gas ratio, and that's what you see here. This black, the thick lines here are what the regions where I can constrain the dust to metal ratio well. It's a function of metallicity again. And the grey shaded area is just taking the Milky Way, a large range of sight lines in the Milky Way, and scaling metallicity. And that does a very good job. And so the corollary of this is that part of what I talked about is not so important. But I did not know that. Okay, and it is an important point to note. Okay, so the scaling the dust to metal ratio, dust to gas ratio with metallicity seems to be a very good description of what we see in distant galaxies. The different lines here are different ways of extrapolating. And so that so you would now ask, how does that compare to other people's measurements? So this is what people get when they model dust emission. Okay, so now these solid lines are from 200,000 galaxies averaged together. These are individual galaxies in the nearby universe where people have modeled the spectral energy distribution. And so the overall trend is there is an agreement. I wouldn't necessarily say that there is a correlation in the observational data, but that's what usually is said in the literature. So I think at least there's certainly no evidence that the 2 disagree systematically. But what I really wanted was gas masses. So let me move to that. And really this is a question of how well does it work when you compare. And so how do you test this? Well, the simplest way, the most direct way to do it is to take these spectra, okay, which are small bits and pieces of galaxies. And here's an example from SDSS. This is actually a failure in SDSS, but there's an early version of SDSS imaging pipeline that thought that this galaxy actually was 250 pieces. There was a high correlation function around here. So for each of these red dots we have a spectrum. I can measure it spectroscopically, the gas content. Then I also have an H1 and a CO map from which all is fallen out here, from the Things and Heracles survey. And from there I can get H1 and CO, or molecular gas, and do the same thing for indices 6 to 8 using a mosaic from the Ping survey. And then I can compare directly the 2. And so this is what you get from M101. This is directly measuring from the H1 map only here. And this is what you get from the spectroscopic measurement. And this is how I did it first, because I actually only had the H1 map first. And I had a bad outlier. Okay? This is okay correlation. It's a factor of 2 scattered around. This outlier turns out to be the center of M101, where there is no H1. So it has CO, so you add the CO, and as luck will have it, I think this is more luck than design, it moves straight onto the correlation. So that was quite satisfying when that happened. And then you can add in more galaxies, look at deviation as a function of gas surface density, equivalent width of H alpha, color, H alpha to H beta. Generally, it works well to within a factor of 2, which is the 2 lines around here. But it breaks down. It just doesn't work at high surface densities. It's not going to work, it's never going to work, because the problem is, when you go to sufficiently high surface densities, you have a lot of gas, and the only thing you're going to see is the stuff that's in front of that gas. It's not going to probe what's behind it. Okay? So this only works if you have a good mixture of massive stars. So there it breaks down. So this is a useless method for anything in general in central part, very, very extreme central parts of galaxies. I think I'm actually going to skip over this. This is just a complete comparison to other methods. It's mostly to make myself feel good. Now, just to summarize this very quickly, to apply this, you really require rest frame optical spectroscopy spanning between these lines. It does seem from the tests we've been able to do, there are some more tests that I haven't shown, but in general it seems to work, give you a gas surface mass density within a factor of 2, which is about as good as you can do in most of the direct method as well, in this range. Okay. So outside that range you're not going to do a very good job, so don't think about this for the very extreme outside of the galaxy, and don't think about it in the very nuclear parts of the galaxy. It's not going to be perfect. But it has some advantages. It's independent of the CO to molecular gas conversion factor, and it measures gas spectroscopy and star formation rate in the same aperture, although with some covariance between the parameters. So it's not suited for high density, it's not suited for galaxies with little or no star formation, so you really should view this as a complement. Okay? I'm not offering this as an alternative to other methods, but it is as a very useful complement, and you can use it for very large samples. So let me just move to that. And when you read the literature on SDSS, you'll find a very large number of people moaning is probably not the right word, but complaining about the aperture effects, which is the fact that you have these 3 arcsecond fibers. And to some extent they're right, but I think it has certain advantages because you know quite well which region of a galaxy you're actually getting your data from. So you can use it and combine it with redshift, because as you move up in redshift, you're going to look at different sized apertures. So here's then an example of what I showed you earlier. On the y-axis, I have the gas mass divided by the mass in stars. On the x-axis, I have the mass in stars. Now this is the plot I showed you earlier, but then a scatter plot. And the data points I showed you earlier from the gas survey are in red, and the blue are from the alpha survey, and they are the same in every panel. And each panel corresponds to different redshifts. So these are different projected sizes of the 3 arcsecond apertures. Okay, so here it samples only the central 1 kiloparsec, that's what the cartoon illustrates, and you move out in redshift, you sample a larger and larger fraction of the galaxy, and what you see is that this grey shaded area, which is what I'm getting from the SDSS, well, here it's in the central region, there's less gas, more stars, they are below the total values, but as you move out in redshift, you sample a larger and larger fraction of the galaxy, you approach the total values. So by doing that, in theory, you can actually use this technique now to invert and get the profiles of gas as a function of the galaxy type. And I'm not showing that because it's a very complicated thing to do well. But you can now then move, this was gas content, and it's not particularly exciting, so it goes down, basically. And I'll show you a more sophisticated version of it in a second. But another quantity which is even more crucial for evolution is how quickly will it run out of gas. Okay? So that's the gas mass divided by the star formation rate. And we looked at this in the gas survey. I'm sorry, I should have cut out the left-hand panels because they're not important. But here's mass in stars again, star formation rate divided by gas mass. So that's how quickly, well, it's actually 1 over the time it takes to run out of gas. And what we found in this paper was that it was actually quite a constant number as a function of mass. And we interpreted it in this paper as being due to some sort of regulatory feedback cycle in the galaxies. But that's just on large scale. So what you would really like to do is to understand how this varies between large, which is the reservoir of gas, if you will, and the central parts of the galaxies. And then we can do that by combining this information from the alpha survey, which is the big size, it's 3.5 arc minute beam with a receiver, and 3 arc seconds spectrum from SDSS, so that's really large and small. And this is what you get if you do that. Okay, the red are now the depletion times, in this case in years. The blue dashed line, just to guide your eye, is the Hubble time at the mean redshift of the galaxies that went into the plot. The red points are then the total reservoir, and that's quite close to having a depletion time of the order of the Hubble time. The grey points here are now what you get from the central region. The green points are from another survey done up the hill here, which I just put on as a sanity check. And you can see that firstly, it's much lower than the depletion time of the total reservoir. It's the same galaxies that go into everything here. And it's also much shorter than the Hubble time. So in order to sustain something like this, you definitely need to feed the central regions significant amounts of gas in order to maintain star formation. Otherwise you will run out quite soon, and it's unlikely that you're observing the universe in such a special way. So that's sort of the simplest way you can illustrate the large and small scales. So now I want to move away from this because this is difficult to extend to very large samples because we don't really have the data for very large numbers of alpha galaxies. So instead I want to just present an inventory of gas, okay? And showing that the picture, now I've been plotting X against Y because that's easy and is easily explainable. And I'll try to convince you that it is oversimplifying too much. Okay, so now I'm going to just look at the central parts of galaxies, but I'm going to give you an idea. So I'm going to look at galaxies where I'm sampling about half the total light of the galaxy. And I'm going to plot this slide is a completeness diagram, which I'm happy to explain if somebody really wants to know, but let's focus on the left-hand side. It's prettier and easier to explain. So in this case, I'm plotting stellar mass, and here I'm plotting stellar surface mass densities. That's the mass divided by the size of the galaxy squared. And it's colored according to the gas fraction. So blue has high gas fraction, red has low gas fraction. And you can see in this case, there is not a very good correlation with the mass. Okay? There is clearly a good correlation with the stellar surface mass density. That seems to be a much more closely related quantity. And that's similar to what we found for the gas results I showed you in the introduction. You can do another plot, which is now here star formation rate per mass. So that's star formation activity in galaxies as a function of mass. And if I now fix mass and I go from the bottom up, what you see is that the gas fractions go up. So the galaxies that are more strongly star forming at a given mass have a higher gas fraction. And that's not unreasonable, because you need gas to form stars. But it's certainly very difficult to get this kind of trend out of the data sets that are not as large as the SDSS. You can also do the same thing, but now for depletion time, so gas divided by star formation rate. In this plane, mass, stellar surface mass density, the trends are very similar to what we saw for gas fractions. But when you come to this, which is the star formation activity, you see in this case the depletion time. Okay, these were the gas-rich galaxies, but their depletion times are very much shorter than the gas-poor galaxies. Okay, so they have higher gas content, but they're also going to run out of gas very quickly. So the question is whether there is some sort of equilibrium relation here, and so these galaxies are basically out of equilibrium in the feedback cycle, and they're going to reduce their star formation rates and use up gas, drop down in this diagram to lower star formation rates and also lower gas fraction. I don't know. So that's the basic inventory. Now let me turn to applying this to something that is considerable interest, namely the mass metallicity relation. So for those who haven't seen this is a relationship between stellar mass and the oxygen abundance of galaxies. And there is a correlation increasing, and then as you go to high mass, it turns over and flattens. And then what has been claimed, so this is relatively robust, I think this one, most people agree on this, but what has been claimed, and there's been quite a lot of work on this in the literature, is that there is a relationship. If you go off this relationship, it correlates with star formation rate. This is a paper, very influential paper, came out a few years ago by Manucci et al. And they took this metallicity relation and then they split it by star formation rate, that's the different colors, and they say, look, it correlates a lot with star formation rate. So if you have a high star formation rate, you have a low metallicity at that mass. If you have a low star formation rate, you're high up. And so this has been very influential. It's been, a lot of people have been working on this. There's been a few papers that claim there is no such relationship using other data, but from the Sloan, it's generally been sort of taken as given. This is how it is. Okay? And so I decided to have a look at this in more detail. I think I'm going to skip over some of these philosophical comments. And I used a different, so there is, well, I guess I should make one comment. So when you're taking an indicator, so a metallicity indicator, something that tells you from a line ratio, this is the metallicity of a galaxy. If you just take that, if you just take one line ratio and you get a metallicity, okay, there's going to be some, it's not going to be the full story. We know that any Strömgrenz figure is going to be characterized by at least its ionization parameter. So it's at least going to be two parameters, metallicity, which gives you the ionization flux, and the ionization parameter, which tells you something more, that are going to influence the properties of your H2 region. So if you take an abundance estimator and you ignore the fact that it also depends on ionization parameter, well, it's probably okay if you're just going to get a mass metallicity relation. It's just going to add scatter. But if you're going to look at deviations, okay, why is it changing metallicity? Okay, then you have to care about secondary effects. So you have to care about other parameters that come into calculation. And so that is very important when you do this kind of check. Okay? You want it, otherwise you can get the wrong results. So this depends a bit on the kind of abundance estimator you use. And so here I used another one. This is using Doppiter et al. 2013 as recent models from that group. But it would also work with other list indicators. And here, different colors are again different star formation rate, and although it looks different than from the Manucci results, there's still a plane here. At least if you twist your eye a bit, you can see it sort of curving after a few beers perhaps. But there is a plane here. I haven't tried to fit it because it's not very interesting. But the problem is that what everybody seems to do is they take one paper and they say, okay, if I sample so much of the light of a galaxy, the metallicity I measure is the total metallicity of the galaxy, whatever that means. But if you look here, this is the mass metallicity relation now using full likelihood distributions. Here I colored it by star formation rate, the average star formation rate in each bin. And here I colored it by the size of the aperture I'm looking at. Okay, 3 arcsecond aperture. The trends are very similar in these cases, so it makes sense then to take your galaxies and now do the same exercise, but make sure you look at the same size region of a galaxy, because galaxies have metallicity gradients, etc. So there's various ways you can cut them. Here I've binned it in size relative to the half-light radius of the galaxy, and I've plotted mass metallicity relations, different bins here in size, colored according to the star formation rate. Okay? So now, here you can see how the star formation rate really correlated with the position. If you fix yourself to look at the same aperture, I don't see a lot of correlation anymore. Okay? There isn't much left. There is a little bit at high mass, which interestingly enough, in the literature is generally the mass range where it's claimed there is no correlation with star formation rate. But low mass, certainly I see no dependence on the mass metallicity relation on star formation rate. So, and there's ways to sort of try to understand this by making simple models. It partially comes down to how metallicity gradients influence emission line profiles. I think it's a bit technical to go into details, but still, people will say, well, that's sort of meaningless when I look at high redshift galaxies or even low redshift. There is scatter in this mass metallicity relation. So what causes that scatter? Well, that's where the gas masses come in. So that's what I actually wanted to look at when I started at this, was to look at what happened when I put in gas content. So now I split, not colored by star formation rate, but rather by the gas mass. Okay? The gas mass in the region I'm looking at within that galaxy. And so here there is a strong relationship. Okay? There's a strong correlation at a given mass with offsets in the mass-metallicity relation with gas content. Okay. And I'm not going to go into a theoretical interpretation of that because almost all the existing modeling that's been done at the moment have assumed that there is a relationship with star formation rate, not with gas. There's a few that do find a little bit of a correlation with gas content. It's the one from Simon Lillis' paper now in the spring, where he claims there is a lot of dependence on the gas fractions, which I have plotted here. But there seems to be that this is a much stronger effect than the star formation rate effect. And if you think about it, that might be a bit surprising to you, because there is a relationship. It's not a law, even though some people call it a law. It's a scaling relation between star formation, surface density, and gas surface mass density. Since I'm talking about total gas masses, this is the appropriate relationship to use. And it's slightly non-linear. So you would expect that any offset in the gas, if you use gas to split, should be weaker than any effect due to star formation, because you would basically lower the power. So that brings me to the last point of this talk, which is to ask whether does actually, that's sort of a central check here, whether the fundamental scaling relations that we generally find actually holds in this case. So this is a topic that really been well studied in this place. I'm not going to talk too much about this. This is a plot from, aged plot from Frank Vigil et al. Plotting total surface mass density in gas. The more popular these days is to just plot molecular gas. And surface star formation rate density on the y-axis. And there is a correlation here with a turnover of low surface densities. Now, if I do that now with the SDSS sample, and I plot this split by gas fraction. So there's a story behind this. The first time I did this, I didn't split it, I just took everything, banged it together, and I found no correlation, and I was completely depressed, and I put this paper on somewhere else. And this, nothing happened for a while. And then I thought, well, there's a lot of variation in this, so I'll look at it, what happens if I split by various parameters. And so here I'm plotting now in 9 different bins in gas fraction, the star formation rate versus the gas content, and the green line is the same in every panel. Now what you see is that there is a correlation. The correlation is actually somewhere between 1.4 and 1.2 in slope, but that the overall normalization changes systematically in the gas fraction. So there is the scaling relation, slope is consistent at every gas fraction, but the amplitude isn't. And it also tells you that the most gas-rich galaxies, in this case, have the least efficient star formation. This is how it goes if you can convert it into star formation rate over gas mass and plot it as a function of gas fraction, and you think, ooh, okay, that's very close to a slope of 1, so maybe this is a method. Maybe there's a problem with the method. So I went and used a number of different data sets, where here's M51, it's a beautiful galaxy, which I just was told is the inspiration behind the house from Astronomical on the hill. This one, we have star formation rate, we have gas masses, we have everything ready from other people using completely different methodology. No particular reason they should agree with what I did for the SDSS. And this is where they lie on top of my data. So the correlation is actually quite good. Okay? Completely different methodology. So you might think, oh, that's interesting, but it's a very old result. There's a pair of papers from Doppet and Ryder back in the mid-90s where they proposed this kind of scaling relation as an alternative. It kind of went out of fashion, probably because there are 2 variables on the one side. There was another paper recently by Xi et al., where they also looked at nearby galaxies, finally, this kind of scaling relation. This isn't very useful because this one basically tells you if there are no stars around, it will have no star formation, and that's probably not going to be right. This one does work well in the limiting regime. So you can do a couple of possible scaling relations. So let me just focus on one, which is just assume that the star formation rate depends on just a local free fall time scale. So the gas surface density, the scale height, and the total mass in stars and gas. And the scale height we can get from other observations. You can also conclude in the fit. And when you get that, you find that all the data here is well represented by a fit of this form, which is essentially given by the local free fall time plus the observed scale height of the stellar disk. And that fits pretty much as well as anything, and it also gives you a changing scale, overall scaling due to the stellar content, which have to contribute to the total gravitational instability of the system. So I'm going to close there. I don't think that is probably controversial. Last time I presented it, nobody believed me. So I'm going to leave. I'm sort of over my time, so I'm going to leave here with a brief summary. Basically saying that this kind of optical technique can give you gas surface mass densities within a factor of 2. I think where you really would look at it is really think about it as a complement to other methods. I think that's where it has its greatest power. I think the fact that depletion times and gas fractions and the general inventory of gas in galaxies are not functions of single variables. You have to take that into account when you think about galaxies. I'm fairly confident that the mass-metal-history relation does not depend strongly on star formation or when you take proper account of aperture effects. And I think that's interesting. Let's see what the impact is. I think many people will disagree with me. And I'm less confident, but still happily putting it up here. It's, committing myself to video, that the star formation or scaling relation is better described as a function of the local free-fall time scale than just the gas content. So, thanks.
So, do we have any questions? And it's always students first.
I have two questions actually about the methods. The first is, did you explore the effect of a varying extinction curve?
Yes, I did do that. I tried both the total slope, and so that if I change the slope purely, then it basically leads to high. If I make this attenuation curve more shallow, I get higher gas densities. If I make it steeper, I get lower gas densities. That's a pre-parameter to a certain extent. I tried a couple of more sophisticated, more recent publications. So one by Chevaillat et al., which is trying to fit a large number of radiative transfer models, and that gives very similar results to what I showed here, but at a much higher computational complexity because I introduced one extra free parameter. But yes, I tried to do that. And if you allow the overall slope of attenuation curve to freely vary, then you can get what you want, pretty much. But of course that we wouldn't do that because we know roughly what the slope is. So, but that is an uncertainty. So.
The second question, I don't know if I understood well, but are you assuming that the metal depletion into the dust is the same in the region that is doing extinction as in ionized gas? Because that might be a big problem, especially for the oxygen, right? Which is also the metallicity that we take.
I cannot distinguish. So it is an effective average depletion along the line of sight, essentially. But yeah, it's essentially this will be in the ionized region. It's hard to know whether it would be. It is an average. It's a weighted average, a luminosity weighted average depletion between the ISM and the ionized gas. You cannot from this kind of modeling identify where the depletion is isolated.
Because I think from very nearby studies, I think the oxygen abundance that goes into the dust is the one that has the strongest density determinant.
Yeah,
so
so
a tricky one too.
it is a bit tricky. So I did actually look, it's in the paper I think, I did look at the depletion as a function of dust attenuation at fixed metallicity, and so the depletion are higher and higher dust attenuations, similarly to what you see along Milky Way sightlines, where you also see a correlation between depletion and total attenuation, but I've never tried to put the two together because the methodology and the way you interpret it is also very different, but the correlation is there. The trend is consistent with what you see in the Milky Way in terms of depletion along sightlines, but I'm not sure whether it translates into an answer to that.
Sure. Yeah. So early on, you suggested that the stars form out of molecular gas. But then when you showed us these plots of the alfalfa and gas surveys, those are predominantly surveys of atomic hydrogen. And then you showed us that the depletion time gets shorter in more massive galaxies. That's a depletion of atomic hydrogen, not of the total gas content. And the more massive galaxies are better able to convert their atomic gas into molecular hydrogen. So how exactly are we supposed to interpret the decrease in depletion time at high stellar mass when in cold gas survey and in things in Hercules we see the opposite? And what role then does not just the gas fraction play, but the molecular gas fraction?
So in this case, that is, I think, if we just look at the total reservoir, it is probably the dominant gas in these galaxies. It's probably dominating the total gas mass. But you cannot say that this, in this case, is the gas that's turning into stars. Okay. So that's in this case, it's actually very difficult to relate that to the molecular content because we don't have molecular gas masses for this, so you can't really say it. But in this case, I don't think if I put total gas mass here, I don't think these numbers would change very much because we're really talking about galaxies that are atomic gas rich. So they're unlikely to be molecular gas dominated. If I put on here molecular gas divided by star formation rate, indeed, in that case, these values would drop down significantly and probably drop down to this region. So in this case, I would say I wouldn't interpret this depletion time as being a causal link. I would interpret this as being the reservoir available in order to transport gas into the central region as a total link. And I think to fully interpret it, this is actually a good point which I should have mentioned earlier. A major limitation of this methodology that I was just presenting is that it doesn't distinguish between atomic and molecular gas. And that makes it complicated to interpret. Okay, so you have a trade-off. You can get it for a lot of galaxies, but you're going to get something where you cannot say whether it's molecular or atomic. And so that part, I don't think you can easily get around in isolation. And that's also partly why I'm thinking that this is also a very useful complementary method in order to combine it with CO data, because it also will give you an independent constraint on XCO, right? So I think how to interpret this result is actually not, I agree, it's not a trivial thing. I think it needs simulations. You need modeling in order to interpret it. And this is a downside of this method, which I should have pointed out earlier. So it's good that you brought it up now. But I think the fact that you're conflating molecular and atomic gases is a problem. It makes some of the interpretations, particularly the centers of the galaxies, where you will have large fractions of molecular gas, quite difficult.
So when you talk about mass metallicity and aperture effects, presumably your sample is still low range.
That's
So
right.
that observation has been extended out to 2.5. So how can you explain that if it still holds a star formation rate at a higher redshift?
So the correlations with higher redshift aren't very good. Okay, so what people do is they say, oh, if I add, so mostly they cannot do what we can do at low redshift. What they do is they say, if I add star formation rate into my prediction of metallicity, my predicted metallicity differ from the observed metallicity by so and so many decks. And they find that if I add star formation rate in, I reduce the scatter by a small amount, which is typically of the order of 10%. Now, that is actually quite a challenging thing to do, because there's going to be the uncertainties of those metallicity measurements are probably going to be dominated by systematic uncertainties at high redshift. So, and these are not necessarily inconsistent with what I'm finding. Okay, in a massive end, which is what you do at high redshift, you're doing sort of this kind of mass range upwards. Here there is a correlation between star formation rate. So here I would actually anticipate that I would reduce. I should have had the numbers to give you that peak, but the program that was calculating that crashed every single night I started it. So 4 nights in a row. I think I need to relearn how to program. But anyway, so here I would gain from adding star formation rate in terms of predicting the metallicity. But it isn't a very strong effect. And certainly it's very possible that these galaxies, if you had gas mass measurements, it would do a lot better. Okay. But it's not inconsistent with the high redshift stuff. I just don't think the high redshift stuff is very convincing in terms of giving independent results. They basically just say, oh, the high redshift stuff is consistent with low redshift data. But I think if you change low redshift data, they would still be consistent with low redshift data.
Are there any other questions from students? And then we'll go to the young half. Well,
so if I take this plot and compare it to emission, could I determine the typical metallicity gradients in a mass star formation rate sample?
If you're very good at doing numerical differentiation of complicated poorly sampled data, yes. We tried. It is actually a bit difficult to invert. In principle it is, yeah, because it is as an integral of the metallicity. In principle you can invert this to get the metallicity gradient out. In practice it's quite numerically unstable. So we haven't found a very good way of doing it, but it might be doable.
okay, and now the paper is open.
I wanted to ask about your third result on your conclusion slide. That at a given mass scale, galaxies that have particularly little gas have gas of high metallicity. Right? Right? If you have little gas, it's of high metallicity. I've always had a very naive interpretation of that. Galaxies that have little gas are the ones that haven't gotten recent fresh cold gas supply, while the stars continue to pollute. So if you have constant pollution but it hasn't rained recently, whatever stuff you have is highly polluted. Is that qualitatively one of the aspects that plays a role there?
That would be my. That could possibly be the case. So it's my guess that that's what happens. But this is relatively new. I'm not sure, and this is sort of this is actually how the mass metallicity star formation rate relation was originally interpreted as well.
Right.
Some sort of infall of pristine gas pushed you down here, and so my guess is that that's indeed what happens. Is that in fact, I haven't plotted that here, but you can convert this into yields, and you're finding that these galaxies that are up here, they lie very much on the predictions of a closed box model. So in that case, you will have this constant re-ejection of metals, and metallicity would indeed go slowly upwards, and you would have reach that plateau. And so that's where the upper limit here is actually very close to what you get. If I plot this by gas fraction, that's actually what you get, because that's how the closed box model limit is. It's a function of gas fraction. So I think that's a very likely explanation, but I can't give you any substantive argument for it in addition.
I must confess, I'm still trying to understand your first few slides.
Mm-hmm.
And I guess my question is similar to Sharon's question. So you're looking at ionized lines. But then you say you infer from that the entire gas mass including where you have a big mixture of ionized regions, cold regions, H2 that may be traced by CO, but 50% is probably not traced by CO or all these traces. So my question then would be, what actually are you seeing and how reliable are these determinations given that you have this whole range of different environments that is thrown into one thing?
Yeah. Okay. So that was a question I hoped I wouldn't get. No, but that's a very good point. In fact, this is something that. Okay. So the way I actually do the derivation, and I haven't gone through that here. The only way that derivation is meaningful is in an angle average sense. Okay. So the actual derivation, which I skipped over here, assumes all the calculations assume that what I'm getting out is the angle average across the entire sphere around the galaxy. Okay, and then that's where the assumption about the Poissonian mixture of clouds comes in. So if you have an angle average around that, you can get around many of those nasty aspects that you're pointing at. So in principle, if you're looking at a single line of sight in a single galaxy, face on like this, you have, and so the regions are relative, they're intermediate size. They're typically 3 kiloparsec or so, right? So they're not the entire galaxy, but they are not the non-trivial amount. So formally speaking, this method is only applicable in an angle average sense, and in that case, I would say the only way I can really say anything sensible about it is when I have 1,000 galaxies that I average together. So in fact, it took a long time before I was willing to try to make that method tested on a spatial resolved galaxy where I'm looking out along a single line of sight, because formally speaking, the derivation is not valid. So the concern is real. I think that that's why I think the proof is in the pudding in a way, in that case. That it happens, it seems to work well in the resolved case, and I wouldn't say that the arguments that are put down in the paper are valid. Okay, so this is what you're saying is entirely right. I'm not going to deny that at all. It really is a question of an angle average solution. And so for application to something like SDSS, where you have a very large number of galaxies, I was fairly confident that would be appropriate. But it now seems to work well for the resolved case as well, and I'm not sure exactly why that is. Maybe I'm just sampling enough sidelines. Maybe there's something I don't know. I honestly don't have a very good answer to that question, so, which is why I was hoping nobody would ask. But it is a very valid concern.
Do we have any other questions? Okay, then I think with this new approach and in collaboration with Rob and the other people in the city, we will thank the speaker again.